Hello, today we're going to talk about geometric transformations, which are defined to be anything that changes the size, shape, or position of a figure to create a new image. There are four basic types of transformations, and the first one is called a dilation. Dilations are a little bit unique in that they actually change the size of the figure. It actually gets smaller or larger, and because of this, they're often called a shrink or stretch transformation. The second type is called a translation, also known as slides or shifts. They're called this because the figure simply changes position by moving in a certain direction by a fixed distance. The third type is called reflections, also known as flips, because the figure is actually flipped over a line of reflection to create its image. And the fourth type is called a rotation, also known as a turn or a spin. And in this type of transformation, the figure is actually rotated around a fixed point that we call the center to create its image. I'd like to take a second to talk about the notation we use for transformations. We say that some object, let's call it triangle ABC, after it has been transformed, we use what we call a prime to describe the image's point. So first of all, the figure that we start with is also called a pre-image. It's the figure we have before the transformation. And after it's been transformed, we call it the image. And so like I said, you would actually read this as A prime, and then B prime, and C prime. That's how we say it verbally. And if we were to undergo more than one transformation, the second one would be called a double prime, and B double prime, and C double prime. If that would, I guess, be called the image of the image. So I do want to get that out of the way before we go into more detail. I'd also like to talk about the last three we just talked about. They're called rigid transformations, and that's our translation, reflection, and rotation. And the reason they're called rigid transformations is that their size and shape is preserved, which you probably remember that if you have two figures that have the same size and same shape, we call them congruent. So this is also often known as the congruence transformation. And it's these rigid or congruence transformations that I want to talk about in more detail. And we're going to start with translations. Okay, and we're going to start with translations, which are defined to have every figure moved in the same direction by the same distance. We say that a translation preserves orientation. So what you're looking at here is image and pre-image. This triangle has been translated up and to the right, and let's just say it's been moved up 2 units and right 4 units, although obviously I haven't measured or anything. But you can see that this triangle has clearly been slid or translated to the right and up. First of all, the reason we say that it preserves orientation is because of the relationship between vertices. So you notice if we were to describe in clockwise reading each vertex, A goes to B, B goes to C, and C goes to A. In the image, that exact same orientation exists. A prime leads to B prime, leads to C prime, and then back again. So that's what we mean when we say that it preserves orientation. And we're going to talk about some other types of transformations that do not, like a reflection. But let's look at the details of our notation and how we can define a rule for this. Being able to describe that the translation is to the right 4 and up 2 is great, but we'd love to have some algebraic notation. And so we have two basic options. One is to look at some point xy, and we want to describe it in general, right? I don't want to just describe one point, I want to describe any point. And so I know that if I've shifted to the right 4 units, that my x-coordinate has added 4 to its x-coordinate, and my y-coordinate would have increased by 2. So one way we can do this is here on the left here. We can say that xy and just draw an arrow. It becomes the new point, x plus 4, y plus 2. And this is the most common. That's what we're going to use the most. But I also want to at least make us aware that we could use kind of a function notation. And it's not the same as function notation, but what it's saying is if my input was some point xy and it underwent transformation t, that the new point would be x plus 4, again, because I've added 4 units to the x-coordinate, and y plus 2 because I've added 2 units to the y-coordinate. So let's look at some specific examples and see if we can knock this thing out. Okay, so our first example here shows that we have some quadrilateral, looks like a rectangle, CRKI, and we want to translate it using this rule, x minus 5 and y minus 2. So we know that if I'm subtracting 5 from my x-coordinate, then I should be moving to the left 5 units. And if I subtract 2 from my y-coordinates, then I would be shifting down 2 units. So we can do this a couple of ways in terms of actually performing this translation. We can just take any point and count. Take point C, for example, and go 1, 2, 3, 4, 5 left and down 2. And there would be my new point C prime. And I could do the same thing for R, 1, 2, 3, 4, 5, and down 2. And there would be R prime. Or we can actually find the coordinates. So say K right here has the coordinates 5, 1. And if I literally do the algebra of subtracting 5 from the x-coordinate, I would get 0. And subtracting 2 from the y-coordinates, I would get -1. And so if I went and plotted the point 0, -1, then that's where K prime should be. And that should be the same as me counting 5 left and down 2. If I did the same thing with I has the coordinates 4, 0. And that means I prime would have to have 4 minus 5 is -1. And 0 minus 5 is, minus 2, because we're down 2, is -2. And so if I had the point -1, -2, that should be the location of I prime. And then once I have my vertices, I can connect them, and that should be the image. So we can look at it algebraically by looking at the numerical coordinates, or simply by counting if it's something simple like that. Let's take a look at example 2 here. Here we have a figure and its image, and we want to write the rule. So the first thing we need to do is determine how much it's moved by. So this point A, for instance, is at -6, 1, and A prime seems to be at -2, -8. So that means, at least for point A, that it's been shifted right 4 units and down 9 units. So one thing that's true about translation is that every single point should be moved by the same amount, right? So if I check C and I go over 4 and down 9, and I land on the right place, and B is at -2, moving to the right would be at +2, which works, and moving down 9 from 7 is at -2. So we see that this same distance and same direction is preserved for every single point, even if I picked some other random one like this point here, which is at -4, 4. That means there should be a point on this triangle that is at 0 by adding 4 to that, and -5 by subtracting 9, and we see right there that there's that point. So now we have to just define the rule for this, and we would say that there are 2 ways. One, we could say that xy becomes the point. Moving right 4 means I need to add 4 units to my x-coordinate, and moving down 9 means subtracting 9 from my y-coordinate. So that would be one way to do it. The second would be, again, using that function notation, t of xy is equal to, and what's on the other side of the equal sign is the exact same as the other methods. So don't even think of these as different. It's just instead of an arrow, we have an equation, an equal sign, and we have that t in front to just remind us that it's a transfer. Okay, so there's our notes on translations, the first of the rigid transformations. And we'll be right back with reflections the next day or two.